Nernst equation. Nernst equation is used to mathematically write the electrochemical cell or the electropotential of electrochemical cell. So cell potential of, this is for a half cell, first we write, it will be Mn to M, which is reduction potential, equal to standard reduction potential minus RT. R is a gas constant, T is a temperature in Kelvin scale, divided by N, number of electron exchanged during reaction, into Faraday's constant, log natural reduced form divided by initial starting form, Mn positive. This is a Nernst equation for half cell reaction. Remember a point, we consider only aqueous solutions, but the concentration of solid M is taken as a unit. So reduced form or metallic form we consider as a 1. Substituting it, the cell potential will be, we know we are using their cathode side minus anode side. So here is a cathodic is copper 2 positive minus zinc to zinc 2 positive. This is a anodic half cell. This is cathodic half cell. This reaction is combination of two half cell reactions whose addition gives the overall cell reaction. Copper 2 positive get reduced to copper, zinc got oxidized to zinc ions. This is oxidation half, this is reduction half. Now let's write the complete cell equation. This is a cell potential which is equal to standard electropotential of copper minus RT by 2, which are the electron exchange during the reaction. Fluoride constant log natural 1 reduced form by copper 2 positive minus standard electropotential for zinc ions plus, because minus here it got plus sign, RT by 2F log natural 1 by zinc ions. So what we will get? We will get finally zinc. We write the complete equation. This is the standard electropotential of a copper minus zinc, comes up here. Then RT2F log natural. Then we having here copper. Further, zinc 2 positive by copper 2 positive. This is that complete cell equation for Daniell cell. Because zinc ions concentration we saw here log natural, and we have sign negative sign outside, so zinc ions goes up. If we make it a plus sign, RT by 2F, copper will go up, zinc will come down in denominator side. If we substitute the values for R, which is 8.314 joule per Kelvin per mole, and Faraday constant 96,500 coulomb per mole at an ambient temperature of 298 Kelvin, we'll get a modified form 0.059 divided by 2, which is nothing but electrons in exchange during this reaction. Concentration of zinc ions divided by concentration of copper ions. This is the equation for electrode or cell potential at any point of time. Higher the zinc ions concentration, smaller the copper ion concentrations. So accordingly, cell potential can go up or down. Let's take a generalized redox equation where A plus B equation, which happens through exchange of n electrons, converted into a species Cc plus Dt. So for such an equation, what we can write? We know there what we saw, we having copper got reduced to copper ion got reduced to copper, zinc got oxidized to zinc ions, and oxidized form we saw has gone up, reduced form has come down. Similarly, we can write it like that: Cc d raised to power d, a raised to power a, b raised to power b minus RT by NF, which is a standard cell potential, which is a difference of cathodic side minus anodic side standard electrodes. Now, determination of equilibrium from Nernst equation. How we can establish the equilibrium point? Here, x-axis is, or concentration is, log of zinc ions and copper ion concentrations. Here is a cell potential. According to this equation, when equilibrium is there, this part standard cell potential will remain constant. And this will vary according to the concentration of zinc and copper ions. With time, zinc concentration go up, copper concentration will go down. And with Nernst equation, that's what happens. Ultimately, it happens that each cell potential will turns out to be 0. That is the point known as the equilibrium point. Substituting the E cell is equal to 0, what we will get? Standard cell potential will be equal to 2.303 RT by 2F, which is a 2 electron exchange during reaction, log concentration of zinc ions by copper ions. At equilibrium, zinc to copper ions concentration will be Kc, which is a reaction equilibrium constant. And cell potential value we know is 1.1. Substitute it at 298 Kelvin temperature. Reaction constant will be Kc is equal to 2.2 into 10 to the power 37, which so it means the reaction will almost go to completion. Equilibrium point is very high, it lies very far away.